For a long time now, physicists have wrestled with a fundamental question: what actually happens at the center of a black hole? The problem is, our two best theories for how the universe works, general relativity and quantum mechanics, give us completely different and totally incompatible answers. So today, we're going to walk through a paper by physicists Tommaso Bambagiotti and Roberto Casadio, who have proposed a new way to picture the heart of a spinning black hole.
So, here's how we're going to break this down. First, we'll get a clear picture of the exact problem they're tackling. Then we'll look at their proposed solution, this quantum dust idea. After that, we'll see how they actually modeled it, what those models predict, and, just as important, what they can't tell us. Finally, we'll put it all in perspective.
All right, let's get right to it. The whole reason this research is so fascinating is because it takes a direct shot at one of the biggest conflicts in all of modern physics. This is the million-dollar question. You know, we often picture black holes as these simple, static points in space. But the reality is, pretty much every black hole out there in the universe is probably spinning. And that spin? Well, it makes things a whole lot weirder.
And here's where our theories collide. On one hand, you have Einstein's general relativity. It predicts that inside a spinning black hole, everything gets crushed into something called a ring singularity. Think of a ring with zero thickness but infinite density, a place where our laws of physics just completely break down. But on the other hand, you have quantum mechanics. It governs the super tiny stuff, and it basically says that nature doesn't do infinities. It expects a real, structured object with a finite size.
So, you've got this huge gap between our two best theories. How do you even begin to fix that? Well, that brings us to the very specific question that this paper decided to tackle.
Now, the researchers weren't just starting from scratch here. An idea called the quantum dust model had already shown some real promise in getting rid of that pesky singularity in simple, non-spinning black holes. So the big test, the next logical step, was to see if this same idea could hold up in the much more complicated and much more realistic case of a black hole that's actually spinning.
So what on earth is quantum dust? Well, instead of thinking of all the matter that falls into a black hole as one single crushed point, this model imagines it as a series of nested shells of individual quantum particles. It's kind of like an onion. And by applying the rules of quantum mechanics to each particle on each layer, the model manages to replace that problematic infinitely dense singularity with a structured, finite core where physics still makes sense.
Okay, that's the hypothesis. But how do you actually test something that's supposed to be happening deep inside a spinning black hole? Well, you can't, not directly. So you build a theoretical model. Let's walk through how they put theirs together.
First, they started with the standard playbook for a spinning black hole. The math is called the Kerr metric, and it sets the gravitational rules of the road. Into that framework, they inserted their model of nested co-rotating layers of quantum dust. Then came the quantum part. They applied Schrödinger's equation, which is like the main rulebook for quantum behavior, to all those dust particles. And finally, they added in the spin, but they did it as a small correction to the system, using a technique called perturbation theory.
Let me try to explain that. Imagine you know exactly how a baseball flies, in a perfect vacuum. That's your simple, solved problem. Perturbation theory is like then adding in small corrections to account for things like air resistance to get a much more realistic answer. Here, the researchers started with the solution for a non-rotating black hole and added the effects of spin as a small correction. And right there, in that very method, lies the model's main limitation. Because they treated rotation as just a small add-on, the model's predictions are going to be most accurate and reliable for black holes that are spinning pretty slowly. Okay, so we've seen how they set up the experiment and we understand its limits. Now for the fun part. What did the model actually find? What does it predict is happening inside?
The first big result is all about shape. For a non-rotating black hole, the quantum core would be a perfect sphere. But this model predicts that adding spin squashes that sphere into an elongated ellipsoid. So think less like a marble and more like a football.
Probably the best way to picture this is to think about spinning pizza dough. As you spin it, it flattens out and gets wider at the edges, right? The model predicts the exact same thing is happening to the quantum core. It gets squashed along its spin axis and bulges out around its equator.
Now, this next part is really significant. See, the classical picture of a spinning black hole includes this really weird boundary called the inner or Cauchy horizon. It's basically a point of no return where predictability completely breaks down. What this model predicts is that the quantum core, at both its widest point and its narrowest, is always bigger than that problematic horizon. It essentially just erases it from the picture entirely.
So when you pull all these predictions together, you get a totally new picture of a black hole's interior. Instead of all the mass appearing at an infinitely dense point, it grows smoothly from the center outwards. And the two biggest wins here are huge. The model gets rid of the central singularity and that chaotic inner horizon, replacing both with a predictable, finite region where physics still works.
All right, we've seen the exciting predictions. But to be good scientists, we have to be just as rigorous about what this model doesn't show us. Understanding these limitations is absolutely crucial.
So let's just lay out the boundaries. First, and this is the big one, this is a mathematical model. It's not a photograph from a telescope. Second, the dust in quantum dust is a major simplification. Real matter has pressure. Third, as we already mentioned, its predictions get shaky for really fast-spinning black holes. And finally, the model completely sidesteps what might happen in black holes spinning at or near the absolute maximum speed limit.
And to their credit, the researchers themselves are the first to point this out. In the paper, when their math started to get into the fast-spinning territory, they state very clearly that these results should not be trusted. And honestly, that kind of scientific transparency is exactly what gives you confidence in the results that are within the model's comfort zone.
Okay, so we have the findings, and we have the limitations. Where does that leave us? Why does this paper matter, and how does it move the needle on our understanding of the universe?
The paper's conclusion really says it all. This work adds another solid piece of evidence to this growing idea that if you correctly apply the rules of quantum mechanics to the stuff inside a black hole, you can smooth out all the paradoxes and physical breakdowns that classical theory predicts.
What this really means is that they've managed to write a mathematical story about the inside of a spinning black hole that, well, it just works. It's self-consistent. It takes the old picture of a physical dead end, a place where physics breaks, and replaces it with a predictable, if incredibly exotic, region of space-time.
So what can we responsibly say after looking at this paper? We can say that the quantum dust model offers a consistent mathematical picture that resolves the biggest problems inside black holes, but, and this is a big but, it does so specifically within the limits of slow rotation. It's a concrete step, but not the final answer. And it leaves us with an even bigger, more profound question. If the singularity is gone, then the center of a black hole isn't an end to physics. It's the beginning of some new, exotic realm governed by laws we have yet to discover.